So let's look at the situation now. Let's start by looking at linear regression, where our outcome is continuous and we're estimating the mean of the outcome for different values of a predictor x1. And we'll call it simple to indicate that we only have one predictor. And let's start looking at examples in the situation where the predictor is binary, ostensibly where we're estimating two means like we did in the first term and estimating the difference in means. But let's look at this in a regression framework. So after viewing this section, I'd like you to understand that linear regression provides a framework for estimating means and mean differences in a linear equation context, and interpret the estimated slope and intercept from a simple linear regression model with a binary predictor. So for linear regression, the equation is relatively straightforward. The regression models the mean value of a continuous outcome, we'll call the outcome y, as a function of our predictor x1. So ostensibly what we're estimating is an equation that gives the estimated mean of y. We'll represent that here with y bar, the bar over it like we did representing estimated means in the first term, is a linear function of our predictor x1, so we have an intercept plus a slope times the value of x1. So as noted in the previous section, x1, our predictor, can be binary, nominal categorical, in which case it will be represented by more than one x, or continuous, and we'll take on those latter two situations in the next two lecture sections. I want to point this out though, as with everything else we have done this far, we will be using data from a sample, an imperfect sample from a larger population or process. So we will only be able to estimate our everything based on the sample. So to indicate that we have estimates, we should put hats over our intercept and slopes to indicate that they are estimates based on the data as well. And frequently you'll see, even though this left-hand side here is the mean of y, which we previously represented with a bar, just to address the components all the same way, this is frequently replaced with a hat in the written version of the equation. So we're estimating the mean of y as estimated intercept plus an estimated slope from our sample of data times our predictor value. And so for any given value of x1, we can estimate the mean of y via the equation y hat equals beta naught hat plus beta 1 x1. We just plug in our value of x1 to this equation and we'll get an estimated value of the mean of y. And the slope compares the mean value of y for two groups who differ by 1 unit of x1. And since we're estimating means of y, this slope is interpretable as a difference in means between two groups who differ by 1 unit of x1. So let's look at some examples when our predictor is binary to start parsing this and interpreting it in a substantive context. So we know an example we looked at in term 1, we're going to reframe as a regression problem, data on anthropometric measures from a random sample of 150 Nepalese children less than a year old, 0 to 12 months old. And the question we might have is, what is the relationship between average arm circumference and the sex of a child? So the data as is, the overall mean arm circumference is 12.4 centimeters, and it ranges from 7.3 centimeters to 15.6 centimeters. And we're curious as to whether there's different underlying estimated means for males and females. This is the mean for everyone. And the data is roughly half and half, slightly higher percentage of female children, 51% female versus 49% male. So we could look at the box plot for these data. We have the sample means. The estimated mean arm circumference for males is 12.5 centimeters. The estimated mean for females is 12.37. You can see from the box plot that follows, that lines up with what we see. There's a lot of crossover in values, but the values for males are shifted up slightly compared to the values of females, hence the slightly higher mean value. So we know from term 1, if we wanted to estimate a difference in means between these two sexes, we'd simply take 12.5 and subtract 12.37, or do it in the opposite direction if we wanted to compare females to males. Here is what's called a scatter plot of these data, and this is what will be a tool that will be useful when our predictor is continuous, but it really doesn't enlighten us very much when our predictor is binary. What we have here are individual points, the individual values of arm circumference for each child in the data. Each dot represents a single child for males and for females. So we certainly got more detail when we actually saw that displayed as a box plot. But when our XB will be continuous, showing these points in a two-dimensional graphic will be useful. So here our outcome Y is arm circumference, which is a continuous measure. We're estimating the mean of Y. X1 is not continuous, it's binary and in male or female. So how are we going to handle that as an X in regression, this binary value? Well, what we'll do is we'll create a binary X that takes on the value of 1 for one of the two sex groups and 0 for the other. So I'm going to arbitrarily make it take on a value of 1 for female children and a value of 0 for male children. And so what we're now going to be estimating, we're going to estimate intercept and slope to an equation that will give us the estimated mean arm circumference as some linear function of this binary sex. So note, as fancy as it seems to estimate a linear equation, this equation is only estimating two values, the mean arm circumference for male children and the mean arm circumference for female children. So again, we're going to get an estimated slope and intercept such that when we're looking at female children, the estimated mean arm circumference for that group is the value of the intercept plus the value of the slope, because x1 takes on a value of 1 for females. For male children, x1 takes on a value of 0, so the slope won't enter into their estimated mean, and it'll simply be the intercept. So this slope, beta 1, estimates the mean difference in arm circumference for female children compared to male children. It is the difference in the estimated mean of y hat, for a 1 unit difference in x1, as we've seen slopes are in general. But the only possible one difference unit in x1 is a 1 unit difference, the difference between x1 equals 1 and x1 equals 0. So the resulting equation estimated by a computer, and we'll talk more about the estimation process later in this lecture set, is this. The estimated mean arm circumference for a given person, given their value of x1, is 12.5 plus negative 0.13 times x1. So let's look at that slope to start, just interpret that. If you think about it, this is the estimated mean difference in arm circumference for female children compared to male children. In other words, female children have arm circumference on the order of 0.13 centimeters less on average than males. The intercept value is 12.5. This is the estimated mean arm circumference for male children. In other words, children whose value of x1 is 0. So that's equal to 12.5 alone. And then if I take the sum of the intercept plus the slope, so the mean for males when x1 equals 0 plus the difference, this is the difference in the mean for when x1 equals 1 compared to x1 equals 0, the resulting sum is 12.37. So males have an arm circumference of 12.5. Female arm circumference on average is 0.13 centimeters less. So when we add negative 0.13 from that 12.5, we get 12.37, the mean arm circumference for female children. So again, this is a fancy linear equation in which we're only estimating ultimately two values, a mean for males and a mean for females. But it is a line. We only need 2 points to get a line. So what does the resulting regression line look in this sample? Well, if we were to put it on a graphic like this, such that our x-axis was a 0 for males and a 1 for females, the y-intercept for this line here is, and again, 0 is slightly off the axis here, but this is the mean for males, which is 12.5. This is the mean for females here, which is 12.37. The slope of this line is very hard to see, but there's a slight negative slope, and the slope of this line is negative 0.13. So x here is not measured on a continuum, but we only need 2 points to get a line, and I show all pieces of that line here. The coding here was arbitrary for x1. In this example, it was coded as a 1 for female children, and a 0 for male children. The variable x1 could have instead been easily coded as a 1 for male children and a 0 for female children, and we could have fit a very similar regression line. In fact, generally it would look the same, but I'm going to put a little star next to my intercept and slope estimates here to indicate that they may be different values than what we saw when x1 was coded 1 for females and 0 for males. So let me ask you this. Can you figure out, based on the previous regression results given and the information we have, what the values of the slope would be if we had reversed the coding and made 1 males and 0 females based on the same data? See if you can figure this out. I will show how to do this in the additional examples section as well in detail. Let's look at another example we used in the first term and bring this back. We will look at comparing the mean length of stay between patients in our Kaggle data set from the Heritage Health System, the mean length of stay for all who had been hospitalized in the year 2007, comparing the mean for older patients, those who were greater than 40 years old, compared to those who were less than or equal to 40 years old. And so now I'll show these means out to 2 decimal places. So the estimated mean for the subgroup who was less than or equal to 40 years old was 2.74 days, as compared to 4.87 days for the group that was older than 40 years. So a large mean difference in the average length of stay between these two groups. So we can use an equation if we want to put this in a regression context of the form y hat equals b naught plus b1, b naught hat plus b1 hat x1, where y hat is the mean length of stay, and x1 equals 1 for persons greater than 40 years old, and 0 for persons less than or equal to 40 years old. So the results of these data, for these data coming from a computer, is our estimated mean length of stay is equal to an intercept of 2.74 plus 2.13 times our predictor x1. So again, x1 is 1 for older persons, and for that group the estimated mean is 2.74 days plus 2.13 days times 1. When x1 equals 0, the younger group, the mean is simply y hat equals 2.74. We'd take the slope, 2.13, but we'd multiply it by 0, so it would not show up in the equation for those who were in the reference group, the value 0 for persons less than or equal to 40. So this intercept is simply the mean length of stay for that reference group, persons less than or equal to 40 years old. This 2.13, this slope of our predictor when coded this way, is 2.13 days. So this indicates that patients who are older than 40 have length of stay 2.13 days larger than the group less than 40. This is the mean difference in length of stay for persons greater than 40 years old compared to persons less than or equal to 40 years old. And of course, the sum of these two things, 2.74 days plus 2.13 days, equals 4.87 days, which is the mean length of stay per persons greater than 40 years old. And as with the arm circumference data, we could have coded these x's in the opposite way, making the reference group the group that was greater than 40 years old, and the x1 taking a value of 1 for persons that are less than 40 years old. We get different values of the intercept and slope, but the overall story would remain the same. So in general, simple linear regression is a method for estimating the relationship between the mean value of a continuous outcome, our continuous outcome y, and a predictor x1 via a linear equation of the form y hat, which represents the mean of y, equals some intercept, estimated intercept, plus some slope times x1, our predictor. When x1 is binary, this slope estimates the mean difference in y for the group with x1 equals 1 compared to the group with x1 equals 0. And the intercept, b naught hat, is the estimated mean of y for the group with x1 equals 0. In the next two sets, we'll revisit this equation, but when our predictor is multi-categorical and when our predictor is continuous, and the same themes will emerge in those sections as well.